For our very first set of notes, we're going to be practicing how to work with radicals and rationalize, and the reason we're doing that is for our next unit on trigonometry, which is the study of right triangles. We do have to work with radicals. We have to know how to simplify them, how to multiply them, and how to rationalize, which means get rid of the root in the denominator. So for the warm-up, if you want to stop the video and try them and then check your answers, it's practicing working with radical operations. For number 1, we're asked to simplify the square root of 45. 45 is not a perfect square, so this is not going to be a whole number. It's going to be a decimal that goes on forever because it's an irrational number. So in order to simplify this, we're going to make a factor tree and find any factor pair that multiplies to give us 45. For instance, 9 and 5. 5 is prime, so we're going to circle that. However, 9 is not prime. It splits as 3 times 3. So 3 is prime, so we're going to circle those. So the prime factorization of 45 is 3 times 3 times 5. So I'm going to rewrite the square root of 45 as 3 times 3 times 5. And anytime we have a pair of numbers, for instance, these 3's make a pair, that becomes a perfect square because 3 times 3 is 9, and the square root of 9 is a whole number, it's 3. So anytime you have a perfect square or a pair of numbers, you're going to bring the number of the pair to the outside because the square root of 9 is 3, and the number that is left inside is a 5. So this would be 3 square root of 5. You can always check your answer on a calculator by typing in the square root of 45 and look at that decimal and then type in 3 times the square root of 5, and they should be exactly the same decimal. For number 2, we're going to simplify this by multiplying 2 roots together. So in August, when we learned how to multiply roots, we said that you can multiply as many roots as you want by using one root symbol and then combining them together just by multiplying the inside numbers called the radicands. So 8 times 6 is 48. And then again, we have a non-perfect square. 48 is not a perfect square, but it does have pairs and it's prime factorization. So we're going to make a factor tree of 48, starting with any pair that multiplies to give us 48. For instance, 6 times 8. 6 splits as 3 and 2. Circle those since they're prime. 8 splits as 4 and 2. Circle the 2 because it's prime. And then 4 splits as 2 and 2. So if I rewrite the square root of 48 in any order, I'm going to be multiplying these 5 numbers that I circled. So 2 times 2 times 2 times 2 times 3. Anytime we have a pair, it creates a perfect square. And since we have 2 pairs of 2's, if I circle this pair and this pair, we could actually multiply all 4 of these together and then take the square root of that number. 2 times 2 is 4, times 2 is 8, times 2 is 16, and the square root of 16 is 4. In other words, if you brought out a 2 and another 2, you would multiply them together to get 4. What was left inside was a 3, so 4 square root of 3 would be the simplified value. For number 3, we have a root in the denominator. So what we have to do is rationalize, which means get rid of the root in the denominator. So you're going to open up parentheses and you're going to multiply the top and bottom by whatever root you see in the denominator. So the square root of 12. So root 12 over root 12. We are not changing the value of the original expression because this simplifies as 1, because root 12 divided by root 12 is just 1. So if I multiply straight across, I notice that I have a whole number and a root. 4 times the square root of 12. Since they're opposites, 4 is a rational number and the square root of 12 is irrational. You can't combine them. So you just write that as 4 square root of 12. And my denominator, I can actually multiply 2 roots together because they're alike. So a root times itself, we always said, gets us back to the whole number, the radicand, which is 12. Or if you do root 12 times root 12, it's the square root of 144, and the square root of 144 is 12. So from here, if I look at my fraction, I notice there's different routes you can take from here. I notice that I can reduce 4/12. The reason I could reduce 4/12 is because they're alike. 4 is a whole number, 12 is a whole number. So if I divide by 4, I would get the square root of 12 over 3. Now I know that I can't divide the 12 and the 3 by a common factor because the square root of 12 is irrational and 3 is rational. However, 12 does have pairs, so I do have to make a factor tree for the square root of 12. So 12 splits as 4 and 3, and then 4 splits as 2 and 2. So if I look at my factor tree, I could actually show the work of simplifying the square root of 12 using the factor tree. There's a pair of 2's, so 2 will go outside, and what's left inside is a 3. So we're going to write that in the numerator. So 2 square root of 3, and the denominator is a 3. This is completely simplified because 2/3 can't be reduced, and the square root of 3 is an irrational number that you can't simplify any further because 3 is prime. Number 4, we're going to do the exact same route. We have to get rid of the root in the denominator. So we're going to open up parentheses, and we're going to multiply the top and bottom by the square root of 12, whatever's in the denominator. So root 6 over root 6. When I multiply straight across, if I look at my numbers in the numerator, I have a 2, which is the whole number, and then I have a root 5 and a root 6, which are alike. They're both irrational. So the 2 will go in front because there's nothing to combine it with, but I could actually multiply root 5 and root 6 using the same process as we did right here, where you just multiply the inside numbers. 5 times 6 would be 30. And then the denominator, or root times itself, is back to the whole number 6 because the square root of 36 is just 6. From here, I notice that I can reduce 2 6 because these are alike. If I divide by 2, I would get the square root of 30 over 3. This is completely simplified because 30 doesn't have pairs, and I definitely can't divide the 30 and the 3 by a common factor because the numerator is irrational and the denominator is rational. So that completes the warm-up. I'm going to switch the screen here to move it to the next part of the notes. So give me a second to erase this all. All right, for the guided practice here, we're going to look at how to solve an equation when you have a root. This is something that you'll have to be able to do when we get into 30, 60, 90 triangles and 45, 45, 90 triangles, which are called special right triangles. So for number 1, in order to solve for x here, we're just using inverse operations. So to get x alone, right now it's being multiplied by the square root of 3. So the opposite of multiplying would be dividing by the square root of 3. So if you divide the right side by the square root of 3, you have to divide the left side by the square root of 3. So right now we do have x alone. X is equal to 6 over the square root of 3, but like we just did in the warm-up, we have a root in the denominator, so we do have to rationalize. So we're going to open up parentheses and multiply the top and bottom by the square root of 3, whatever the denominator is. When I multiply straight across, 6 is a whole number, root 3 is irrational, so I can't combine those. I just write it as 6 square root of 3, and the denominator, or root times itself, is back to 3. From here, I notice that I can reduce 6/3, or 6 divided by 3, which is just 2, or if you want to show the work where you divide the numerator and denominator by 3. So my final simplified answer here, 6 divided by 3 is 2, so 2 square root of 3 over 1, which is just 2 square root of 3. So x is equal to 2 square root of 3. For number 2, our same goal is to isolate the x. So right now it's being multiplied by the square root of 3. So the opposite would be dividing by the square root of 3. So again, whatever you do to one side, you do to the opposite. So I have x is equal to the square root of 5 over the square root of 3. Again, we have the same issue where we have a root in the denominator, so we are going to have to rationalize. So I'm going to open up parentheses, and I'm going to multiply the top and bottom by whatever I see in the denominator, the square root of 3. When I multiply straight across this time, I notice that the numerator has 2 roots, so I can combine those. Root 5 times root 3 would be the square root of 15, and the denominator, or root times itself, is back to the whole number 3. So this is my final simplified answer. 15 does not have any pairs, and I definitely can't divide the 15 and 3 by a common factor because they're opposites. One's a root and one's a whole number. So x equals the square root of 15 over 3. For number 3, again, our goal is to isolate the x. The opposite of multiplying by the square root of 2 would be dividing by the square root of 2. Whatever you do to one side, you do to the opposite side. So x is equal to 18 over the square root of 2, but again, we have an issue. There's a root in the denominator, so I have to rationalize. Multiply the top and bottom by the square root of 2. So when I multiply straight across, I notice that 18 is a whole number and the square root of 2 is irrational. They're opposites, so I can't actually combine those. I just write it as 18 square root of 2. And the denominator, or root times itself, is back to the whole number 2. From here, I notice that I can divide 18 and 2, divide those by 2, or 18 divided by 2 is 9. So x is equal to 9 square root of 2. Go ahead and stop the video and try the next 3 examples and see if you get the same answer that I do. So for the U try, 1b, I notice that we have to rationalize here, get rid of the root in the denominator. So I'm going to open up parentheses and multiply the top and bottom by the square root of 3. When I multiply straight across, I would get 12 root 3 over 3. And then from here, I notice that I can divide the 12 and the 3. 12 divided by 3 is 4. So my final answer would be 4 square root of 3. For 2b, we have to isolate the x. So the opposite of multiplying by root 3 would be dividing both sides by root 3. So we do have x alone. So x is equal to the square root of 8 over the square root of 3. But again, we can't have a root in the denominator. So we're going to open up parentheses. We're going to multiply the top and bottom by whatever you see in the denominator, which is the square root of 3. When I multiply straight across, I notice that the numerator has 2 roots, so I can combine those. 8 times 3 is 24, so it'd be the square root of 24, and my denominator would be 3. From here, I can continue simplifying. 24 does have pairs, so I'm going to make a factor tree. So 8 times 3 would give me 24. 8 splits as 4 and 2, and then 4 splits as 2 and 2. So if I look at my factor tree, I notice that I have a pair of 2's. So 2 is going to go on the outside, and then the 3 and the 2 left over recombine by multiplying and then give you 6. So all I'm doing is replacing the square root of 24 with 2 square root of 6, and then the denominator was a 3. So this is completely simplified because 2/3 can't be reduced. 6 does not have any pairs. So x is equal to 2 root 6 over 3. For 3b, in order to isolate the x, I have to do the opposite of multiplying by the square root of 2, so divide by root 2. So x is equal to 16 over root 2. But again, we have to rationalize, so I'm going to open up parentheses, multiply the top and bottom by whatever you see in the denominator, square root of 2. When you multiply straight across, 16 is a whole number, square root of 2 is irrational, so you can't combine those, you just write it as 16 root 2. And then denominator, root times itself is back to the whole number 2. So from here, I notice that I can divide these. 16 divided by 2 is 8. So my answer is x equals 8 square root of 2. All right, the back side of the notes. Give me a second to erase this and then find that last set. This last part here, the goal is to simplify irrational numbers without having to make a factor tree. And you can do that by the following. If you know your perfect squares, these numbers here on the right-hand side of the equations, for instance, how come 25 is a perfect square? Because a number times itself gives you 25, like 5 times 5. So if you have these in mind, you can actually simplify the square root of 20, for instance, without having to show any work. Here's how you would do it. So for the square root of 20, since 20 is not a perfect square, your goal is to think of this list of perfect squares. Really, you want the largest number in this list that is a factor of 20. For instance, if I look at this list, 4 is a factor of 20. So keep that in mind. So 4 times what would give you 20? Well, 5. So in your mind, in your thought process, without having to write anything down, you would say, okay, I know 4 times 5 is 20, and 4 is the biggest perfect square. So the square root of 4 is 2. And that's going to go on the outside of the square root symbol because 4 is a perfect square. So the square root of 4 is 2, and the other factor that is not a perfect square is 5. So again, whenever you make the prime factorization of 20, you would get down to 2 times 2 times 5 would be your prime factors if you made a factor tree. And you would say, okay, I circle the pair of 2's because that makes a perfect square, which multiplies to give you 4. So you can use this quicker process to eliminate showing the work. So let's take a look at part A. So 18. So if I look at my list of perfect squares, I'm looking for the largest factor of 18, which would be 9. So 9 times 2 gives me 18. Since 9 is a perfect square, I'm going to take the square root of 9, which is 3. And then the other factor was 2. So again, in your thought process, you're saying, okay, 9 times 2 is 18. The perfect square is 9. Take the square root of 9, which is 3, and then the other factor goes on the inside, which is 2. 50. The largest perfect square, that's a factor of 50, would be 25. So 25 times 2. I'm writing this down just so you can see my thought process. So 25 is the perfect square. So if I take the square root of 25, I get 5. And then the other factor was a 2, so that's left on the inside. Looking at part C, 32. The largest perfect square, that's a factor of 32, would be 16. And then 16 times 2 gives you 32. So the square root of 16 is 4, and then the other factor, 2, stays on the inside. 63. The largest perfect square would be 9, because 9 times 7 gives you 63. So the square root of 9 is 3, and then 7 is left on the inside. The square root of 28. 28, the largest perfect square would be 4. So 4 times 7, so the square root of 4 is 2, and then the other factor is 7. It stays on the inside. Lastly, for 45, 9 times 5. 9 is our perfect square, and the square root of 9 is 3, and then 5 stays on the inside. So the homework is down below. Your job is to complete the homework and then check off the answers here where it says scrambled answers. And then you're just going to take a picture of your notes and then the homework and submit that either on Canvas or on the Remind 101 system for your full credit for assignment number 1.